the code generator has to understand, or the code generator module, the developers will have to be familiar with the target language. So without understanding the target language in its architecture, what are the peculiarities of the machine language and how the registers are being utilized, what type of addressing modes are available. Without this, translation cannot go ahead. So the target language, familiarity with the target language, is required to go ahead with the code generation module. For this purpose, for the later part of this module, we discuss about an hypothetical target machine model. This machine model has load and store operations. It has computation operation. It has both conditional jump and unconditional jump instructions. It is a 3-address machine. The underlying computer is a byte addressable machine with n number of general purpose registers. So with this hypothetical machine, considering this hypothetical machine, we discuss the code generation phase and how the major issues of code generation can be satisfied. Load and store operations. Load operation is indicated by LD. After LD, we have the destination register. And this is the source address. Source address can be a register location. It can be a place in primary memory also. So LD, DST, ADDR. Example, LD, R1, R2. Access R2, take its contents and store it in R1. That is meant by load R1, R2. So here we can see that in this particular instruction, we are using 2 registers. So R2 will be accessed first. Its value will be taken and will be put back to R1. Similarly, we have this ST instruction. ST is for storing operation. ST also has this same order. First, immediately after ST, we have 2 items. The first item is a destination and second item is a source. So STXR, here X is a memory location, R is a register. So value stored in R will be accessed and it will be kept in the memory location called X is equivalent to X equal to R. So load and store operations will have to be done appropriately to translate the intermediate code statements to machine language instructions. See here we have to note one thing. See, LD no more LD will be used as such. LD is a mnemonic of code for our understanding. Remember that in machine language, even LD will be a machine binary code. Everything will be in binary. In binary code, there is no scope for mnemonics. Everything will appear in binary code. But it's difficult to understand a binary code and comprehend it. So for that sake, we rely upon these kinds of mnemonic codes for sake of understanding. Next kind is jump instructions. Go to input is the high-level language statement, say in C, where input is a label. A label is, in high-level language, a label is a literal followed, it will be an identifier followed by a semicolon. So that instruction is represented by BR for branching. L is the label. Label means address of the instruction to where the branching has to occur. So every instruction in primary memory will be having an address. So if we, whatever location we want to move, that address will be kept as here. It's BRL. Similarly, conditional jump, branch on condition. So here we have a branching and there is a condition. Now, this branch and condition, whenever we see a branch and condition, we have to look at the high-level language. If x less than 0, do something. That is our statement. So here we can see that the condition is centered around the value of x. Similarly, here branch on condition, based on which value the condition will have to occur. It will be based on R. So R is a register. So in our case, if x less than 0, so automatically value of x will have to be kept in a register. See the way how register allocation and register assignment decisions have to be taken by the compiler. As and when it encounters if statement, if statements will have to be translated to these kinds of statements, wherein R will hold the value of the conditional code. So these are the issues in front of compiler. Which variable are to be kept in a register and how long it is to be kept. These two things are important. We should not erase that register value and load one thing before the entire use is over. So example is branch on less than RL. L is again the label to where the branching should occur based on the value of R. So if the value of R in R is less than 0, Z less than 0, then transfer of control will be passed to the address called as L. That is how unconditional and unconditional branch instruction works. Next is computation operations. In computation operation, there will be an operator. Opcode will be there, operator. It can be operators like add, and, or sub. Now the result of an addition operation is to be kept somewhere. So we have the destination. SRC1 and SRC2 indicates the values to be processed. 3 address format. 3 address are there. Here, values of SRC1 and SRC2 will be taken and it will be kept back in DST. What about SRC1 and SRC2? SRC1 can be a register. SRC1 can be also a memory location. Both can be used. Value can be taken from a register and from a primary memory location. Now, SRC1, SRC2, and DST, they need not be distinct. Why? Because we know about adding x to x and keeping the value in x itself. There can be such occasions where this will be all of these will be one memory location or one register. So depending upon the nature of computation, either we can say that DST, SRC1 and SRC2 will be distinct, or they can be same. It depends upon the circumstances in which the high-level language program is being written. Now we will discuss about addressing modes. Why addressing modes? Because now we have two kinds of locations where values are getting placed. There are n number of general purpose registers, which are the fastest memory unit on the computer. We have also a set of primary memory locations allocated for this program. So registers, of course, it is named as R1 through R0 through R1, R1, R2, R3 like that. What about memory variables? Our program can also refer to a value in a memory location, and that is typically written by variable names in high-level languages. As we are telling repetitive and as we have understood clearly, every memory variable is tied to a memory location. So that is called as the L value of X. So whenever we have a memory variable, we remember that all memory variables will be in a memory location. Whether that memory variable value will be temporarily kept in a GPR or not is an issue that is with the compiler and the operating system. We don't know about that. What will happen? The first thing is indexed address. It is a form AR, where A is a variable and R is a register. So here now how the address of AR is computed. It will take the L value of A, that means the address of A. Address of A will be taken and that value will be added with the value of R. That is how the address of AR is computed. Here LD R1 AR2. A will be having an address, L value. That L value will be added with contents of R2. Then the contents of this memory location, entire memory location will be taken and stored back to R1. In this case, we can see that it is analogous to arrays. When we declare an array called say int A10, we know that A has a meaning now. A indicates the base address. So it is the same as the address of the first element of the array. So A of 0 and A will point at the same memory location. Then to access an array, an index value is required. Depending upon the index value, position of the array element will change. So here R will take the role of the array index. A will take the role of the base address. So we can see that this index address is ideal to represent array manipulations. Either an array element will have to be accessed or an array element will have to be return a value. Both can be done. Next addressing is integer indexed by a register. See the difference here. See here we have 100 R2. Let us see the previous slide. See here it is AR. We were taking the base address in A. So instead of A constant address is given here, 100. So that is the difference here. Now how the location, this location is calculated. 100 is taken as such. Contents of R2 will be taken. Both will be added. Then the memory location represented by 100 plus R2 will be looked up. Values stored at this address will be taken and it is kept in R1. That is how this operation is being done. And this is analogous to the way we are accessing pointers. When we declare a pointer and we allocate an address to a pointer, the operation is as good as this. So how array operations can be done, how pointer accessing can be done, both things we have corresponding machine language instructions. Then we have two indirect addressing modes, *R and *100R. Here, memory location found, see, R will be taken first. What is R? R is one of the n GPRs. There are n general purpose registers. So, value stored at R, that is known. Now, the memory location found in the location stored in R. So, instead of taking the value of R as such, R will be having, say, a value called as, say, 1000. 1000 will be treated as a memory location, and values stored at the memory location 1000 will be retrieved. In this case, with the value of, this is same as this, but with the value of R, we will add 100. Suppose that the value of R is 1000. R is 1000. 1000 will be taken first. 1000 will be added with 100. We will get 1100. 1100 will be an address in the primary memory. So that location will be looked up to take a value stored in there. So it will be accessed. So this is how this indirect addressing modes works. Now, one constant addressing mode. See here, #100. Hash symbol represents that 100 is a constant. Now, what is happening here? LDR1 #100. R1 will be loaded some value, and that is the value, this is the destination. 100 will be loaded to R1. Add R1, R2 #100. R1, R2 #100. Here, see, destination and one of the source are the same. Add 100 to R1 and put back the result in R1. So it depends upon the way how the program is being written. Correspondingly, the addressing modes will also change to represent the syntax and semantics of the original program. Now we'll see some examples and in 3 address format and how this intermediate code instructions can be represented in the machine language instructions that we have just discussed. Cx equal to y minus z. So before we write this, one thing is understood. The person who is translating this intermediate code is thorough with the way how y minus z is to be evaluated and how the result is put back in x. So here we know that we have 3 memory locations, x, y, and z. And these x, y, and z could be temporary variables or memory addresses. But looking at this assignment, we can see that this assignment operation stores a value in an address. So x could be a memory location, and y and z are again 2 memory locations. And now we know that in a machine there will be an accumulator, and usually operations are being done with the help of accumulator, arithmetic logical unit. So implicitly, we pass values to accumulator and registers. So exactly the same thing will be mimicked here. First, directly y minus z will not be computed. First, value of y will be lowered to R1. Then value of z will be added to R2. Then y minus z will be computed. That is meant by that means R1 minus R2. And result is again put back in R1. SUSS sub R1 R1 R2. Then the result of R1 will be kept back in X. Sees a single intermediate statement. Now it is represented with 4 statements. So we see that the number of statements have increased. Why? Because it is because of the way a machine will compute its values. Remember that a CPU is calculating this at a lightning speed. So we need not worry about these multiple instructions. Our worry is that syntax and semantical correctness of the original source program should be maintained when source code is getting translated to intermediate code and later intermediate code is getting translated to file machine code. Second example is array accessing. So for this, for see this, when we see this table, we will know what is happening in the array manipulation. Here A is an array, int A of, see here we have five elements. So we know that first element of the array is A of 0. Suppose that array is stored at location, starting address is at 100. So 100 indicates A of 0. When you move from the first element to the next element, what's happening? This is 100 plus 1 into 8. Why 8 comes here? Because our machine is a byte addressable machine. Each of these memory locations are of 8 bytes in our hypothetical machine. So when we move from one element to the other, we have to add 1 into 8. What is 1? 1 is the array index and 8 is the size of a word or a location or a value. So 100 plus 1 into 8 indicates A of 1. So we can say that 100 into plus I into 8, where I is the ith location. So this equation, this arrangement, we know how an array is getting accessed, what is the importance of the base address, and how internally the index is used by the architecture machine CPU to access the array elements. Suppose that we have now B equal to A of I. This is again a 3 address statement which was translated from the source code. We know that here we have an index mode of addressing. So see here, initial computation here is not getting the value of AI as such. When an index array address is there, immediate worry of the code generator is to see whether it is in the left hand side or right hand side. See, in assignment operator, what is happening? Right hand side will have to be computed first. Then the computed value will be stored in here. So initially, the place represented by A of I will be calculated. Then from that place, the value stored at A of I will be taken and it is put back in B. See here, initially we have to do this. Array index will have to be multiplied by 8. For that purpose, I is taken in a register LDIR1. Then you multiply the value of R1 with 8, that is this value. It is multiplied with 8 and result is put back in R1 itself. Once this value is available, what we should do? We should add the base address with this newly computed value to get this location. And that's what it is done here. LD AR1. What is AR1? Base address of A will be taken. Value stored in R1, that is I into 8 will be taken. Both will be added. Then the value stored at this location will be taken up and it will be stored in R2. So now we know the value stored at A of I. This value is in a register now, and that value should be stored back in a variable called as B. Whenever we have an array index, remember that whenever we make use of array manipulation in our source program, a similar kind of operation is being done at the machine level. We didn't know about this. And this is how things are working. Of course, we knew about this when we calculated, when we discussed array manipulation in our UG days. From those days, we know how an array works and how an array element is getting accessed. That concept we know is getting actually done by the machine code. And see how quickly the machine will do this. And it is because of all these things when we discuss for optimizing source code, especially loops will be taken care. So if you can reduce at least one instruction from a loop, that too including arrays, we will save a lot of computation that is being repeated, will be being done. Now the reverse of this, A of j equal to C. In this case, we are writing to an array element. C, value of C will be taken and that value will be put back in A of j. What's the worry here now? This value is directly known. It is an address. What about the place where the value is to be stored? It should be computed first. So here, since C is on the right hand side, first C is taken care in assignment operation. C, load the value of C to R1. Later G is stored in a register, value of J. Then that will be multiplied by 8. Now we know why it is being done. Then see here, ST A of R2 R1. R1 is the value stored as C. And A of R2 represents jth element of the array A. Base address at A will be added with value of R2 and that is the place where C is to be stored. X equal to star P. How this can be implemented? Here, value at P is to be taken and it is to be put back to X. Value at P. So P is taken up first. P is stored in R1. What is happening here? P will be having an address, say 1000. So CPU has to refer to the location called as 1000, take the value there and put index. So conveniently, value of P is kept in a register. Then load instruction will store the value stored at P to R2. Contents of 0 plus contents of R1 will be star P. Then that value is kept back in R2. Once that value is available, it is put back to X, ST R2. Now star P equal to Y. Here a location pointed by memory is written in this case. Similarly, star P equal to Y. So here y is stored in R2. Value of P is kept in R1. R1, comma P. Then star P, 0 R1, followed by R2. So this is the reverse of what we have discussed earlier. Writing back to a memory location. This conditional statement, if x less than y go to L, and this is our 3 address statement. X less than y go to L. We know about this, what is happening here. So there is a process going on here. Value of x is compared with value of y. See how it is being done here. LD R1x. Value of x will be lowered to R1. See, directly it won't be compared. But initially, instead, x will be lowered to R1, y will be lowered to R2. Then x is getting x minus y will be computed. Sub R1, R1, R2. X minus y will be computed. Then you will get a value. And based on that value, conditions be taken. Branch on less than 0, R1, go to L. This L is represented by M. This is how an if statement like this is getting translated. So if you subtract x from y, we will know what will happen. Suppose that value of x is 1 and y is 2. When we subtract 1 minus 2, we'll get minus 1. That means if the resultant value, if the value after subtracting x minus y is less than 0, that means x minus y condition will be satisfied. This is how it is, the machine language is getting translated. L is the place where the memory location where the branching has to occur if this condition satisfies. Otherwise, the instruction that is getting immediately after this will be executed.